Hello everyone, my name is Dr. Lakhvinder Kaur and I am Associate Professor at Rungta College of Engineering and Technology, Bhilai. Today I am going to explain our topic optical modulation techniques, advantages, disadvantages and application. I hope to share some valuable insights that will benefit you all. So let's get started. These are the outline of my presentation which we are going to discuss. Introduction to optical fiber communication, its history and evaluation, various modulation techniques, advantages, disadvantages, followed by application and summary. Introduction to optical fiber communication. Fiber optic communication is a method of transmitting information from one place to another by sending pulses of light through an optical fiber. The light forms an electromagnetic carrier wave that is modulated to carry information. It enables high-speed data transmission, forming the backbone of modern telecommunication system. An optical fiber is a dielectric waveguide that operates at optical frequencies. This fiber waveguide is normally cylindrical in form. It confines the electromagnetic energy in the form of light to within its surface and guides the light in a direction parallel to its axis. Now, let us discuss the history and evaluation of optical fiber. Starting with the conceptual beginning, the idea of using light for communication traces back to the late of 19th century, with early experiments in guiding light through bent rod glasses. First optical fiber in 1970, Corning glass work produced the first optical fiber with a loss of 20 dB per kilometer, which was a significant improvement over earlier attempts. Next is milestone in transmission. By the mid of 1970s, practical optical fiber cables capable of transmitting signals over long distance were deployed and developed. Development in telecommunication. Throughout the 1980s, optical fiber technology matured and became the standard for telecommunication networks, replacing copper wires due to its superior capacity and reliability. Advancements in transmission. The development of erbium doped fiber amplifiers in the mid of 1980s allowed for long distance transmission without frequency signal regeneration, further boosting the efficiency of fiber optic networks. Widespread adoption. From the year 1990 onwards, fiber optics become important in global telecommunication networks, providing the backbone for internet infrastructure and high-speed data transmission. Continued technological advancement. Advances such as wavelength division multiplexing in the year 1990 and dense wavelength division multiplexing in the early of 2000 drastically or dramatically increased the capacity of optical fiber system, allowing multiple channels of data to be transmitted simultaneously over a single fiber. Now, let's start with the introduction of optical modulation. Optical modulation is a process of varying a property of light such as amplitude, frequency or phase to transmit any information. Optical fiber is a crucial process that allows control over an optical wave or encoding of information on a carrier optical wave. The inverse process that recovers the encoded information from the modulated optical wave is called demodulation. Optical modulation enables many key functions in optical communication system and networks. It is essential for enabling high speed and high capacity optical communication systems. Now, the basic principles involved in modulation are: modulation is a technique used to encode information onto a carrier wave. First is analog modulation, which varies continuously with the signal. Second is digital modulation. It uses discrete levels to transmit information. Now, optical modulation. Optical modulation involves actively modifying one or more properties of an optical wave or beam to encode information or control its behavior. Similarly, demodulation then extracts the encoded information or desired wave behavior from the modulated optical signal at the receiving end. Optical modulation schemes differs in terms of the following aspects. First is optical wave parameter modulated, method of modulation used, and the material property leveraged, physical effect involves, and modulator device structure. Now let us discuss optical field parameter which is being modulated. The key optical wave parameter that is modulated defines the type of modulation scheme used. Major categories as per modulated parameters are: first is phase modulation. The phase of the optical carrier wave is varied to encode information while its amplitude remains constant. This can be implemented via refractive index modulation. Second is frequency modulation. The frequency of the optical carrier wave is varied based on the message signal, while its amplitude and phase remains unchanged. Next is polarization modulation. Materials related to the vector nature of the optical wave's electric field, like polarization state, direction, elliptically, are modulated. Next is amplitude modulation. The amplitude or intensity of the optical wave is directly modulated while keeping its frequency and phase constant. Absorption and transmittance modulation can enable this. Next is spatial modulation. Special property of the optical wave like mode patterns, beam shape, direction and propagation trajectories are modulated. This requires modulating guided waves. Next is diffraction modulation. Parameters related to diffraction effect like diffraction efficiency and angles are modulated via altering optical geometries. The specific optical parameter modulated determines the type of information encoding possible and the appropriate modulation demodulation methods to be implemented. Appropriate photodetectors and decoding circuitry are also needed to recover the message from the modulated optical signal. These design choices depends on the target application and link requirements. Now let us discuss each modulation technique in detail. So first modulation technique is analog modulation. Analog modulation uses a continuously varying analog sine wave carrier that gets modulated by the analog message information signal. The key analog modulation types are: first is amplitude modulation, where carrier amplitude varies based on the message signal. Second is frequency modulation, where carrier frequency varies based on the message signal. Third is phase modulation, where carrier phase relative to reference carrier phase varies. Additionally, we have pulse amplitude modulation, which uses a pulse train carrier with discrete amplitude levels based on the message signal. So let us start with the amplitude modulation. Amplitude modulation varies the amplitude of a high frequency sine wave carrier based on the amplitude of the modulating message signal, while keeping the carrier frequency and phase constant. Some AI technique properties are high frequency carrier wave with constant frequency and phase. Carrier amplitude is proportional to the instantaneous amplitude of the modulating message signal. Applicable for transmission of audio or voice band message signal. This amplitude variation encodes the full message signal continuously on the carrier wave as an analog representation. Demodulation then recovers this audio or data message signal from the modulated carrier at the receiver end. Next is frequency modulation. Frequency modulation keeps the carrier amplitude constant while varying its frequency proportional to the amplitude of the modulating message signal. Some key frequency modulation attributes are: it has constant carrier wave amplitude, also carrier frequency shifted up or down from center or rest frequency based on the amplitude of the modulating message signal. It improves signal to noise ratio and noise resistance. It is applicable for high fidelity music audio transmission. The analog message signal gets encoded onto corresponding variation in instantaneous carrier frequency. Demodulation then maps carrier frequency back to the message signal. Third one is phase modulation. Phase modulation keeps the carrier amplitude constant while varying its phase relative to a reference carrier phase based on the amplitude of the modulating message signal. Some key attributes are: its carrier wave with fixed amplitude. The carrier phase is shifted from the reference phase by an amount proportional to the instantaneous amplitude of the message signal. The phase is the main parameter which is modulated. The message signal gets encoded as analog variation in the carrier wave phase over time while keeping the amplitude unchanged. Demodulation then maps the phase back to the message signal. Next and fourth one is analog pulse modulation. Analog pulse modulation uses a pulsed carrier wave and modulates the parameter of these pulses based on a continuous message signal. Different types are as follow. First is pulse amplitude modulation. Pulses are modulated in amplitude. Second is pulse width modulation. In this type of modulation, pulse width is varied. Next is pulse position or location modulation. In this type of modulation, pulse position in time shifted. This allows the encoding of analog message signal using variations in the parameter of a pulse train carrier wave. Second type of modulation is digital modulation. Digital modulation has discrete modulation states derived from a digital bit stream message signal. Digital modulation types covered later included amplitude shift king ASK, frequency shift king FSK, phase shift king PSK. Now, the key traits of are: analog modulation enables a better signal to noise ratio for audio or voice signals, but is more noise sensitive. Digital modulation resists noise better and works for computer data streams. First type of shift keying is amplitude shift keying. Amplitude shift keying (ASK) is a digital modulation technique that represents binary data by shifting the amplitude of a carrier wave among the discrete levels. Here, the carrier modulated between two amplitudes, high amplitude and zero amplitude. High amplitude represents binary 1. Similarly, zero amplitude represents binary 0. Amplitude shift encodes the binary message signal. Demodulation detects amplitude levels to recover the digital messages. Second type of shift keying is frequency shift keying. Frequency shift keying (FSK) is a digital modulation technique that shifts the frequency of a constant amplitude carrier between discrete values of encoded binary data. These carriers are modulated between two frequencies. Again, it's high frequency and low frequency. In case of high frequency, it is represented by binary 1 and low frequency represents binary 0. Frequency shifts encode binary message signals. Demodulation detects frequency levels to recover the digital messages. Third is phase shift keying. Phase shift keying (PSK) is a digital modulation technique that shifts the phase of a constant amplitude carrier wave between discrete values to encode any binary data. Carrier phase is modulated between two or more discrete phases. Each phase shift represents a unique bit pattern. Phase changes encode digital message signals. Here, demodulation detects phase shift relative to a reference carrier to recover the digital message. Next is binary shift keying. Binary phase shift keying (BPSK) is the simplest PSK scheme with just two phase states, which is 0 and 180 degrees. Binary phase shift keying have various properties such as the carrier phase flipped between 0 and 180 degree. Similarly, it represents a binary digital modulation 1 bit per symbol. 180 degree phase shift represents the binary 1. No phase shift indicates binary 0 here. So, the binary signal directly modulates the 180 degree carrier phase shifts. Next is quadrature phase shift keying. Quadrature phase shift keying (QPSK) modulates the carrier wave among four 90 degrees spaced phase states to encode 2 bits per symbol. Various QPSK attributes are: first, it has 4 possible carrier phases, which is 0 degree, 90 degree, 180 degree and 270 degrees. Each phase shift keys are unique 2-bit input symbol. Double the bit per symbol is compared to BPSK. Symbols can map to bit pairs directly, and it provides higher spectral efficiency over BPSK. Next is differential phase shift keying. Differential phase shift keying (DPSK) encodes input binary data as carrier phase shifts relative to the various phase rather than a fixed reference. Some DPSK properties are: it has no reference phase required. The phase of current bit interval is shifted 180 degree relative to the previous if the input is 1, and it stays same as the previous if the input is 0. The phase shifts are relative and it is robust to slowly varying phase drifts. The ways of performing modulations. Optical modulation can be implemented through two approaches. First is direct modulation and second is external modulation. Now, let us discuss both type of modulation in detail. First type of modulation is direct modulation. Direct modulation directly superimposes the modulating message signal onto the driving current of an optical source like an LED or laser to modulate its output. It performs modulation and light generation concurrently. Optical source bias current is modulated directly by the message signal. This leads to the proportional modulation of output amplitude or intensity, frequency or wavelength, and phase. Its implementation: the message signal is applied together with the DC bias current to modulate the optical source directly. It is simple and cost effective. But some drawbacks of this modulation is: modulation bandwidth limited by optical source dynamics, it has higher intensity noise, and it restricts available optical source types. Second type of modulation is external modulation. External modulation uses a separate optical modulator, components or setups while keeping the optical source drive current constant. Optical source provides constant intensity output. Separate external modulator encodes the message signals and it enables the independent optimization of optical source and modulator. It has high modulation speed and bandwidth. Similarly, it has lower noise and is greater choice of modulation type. Now, let us discuss the structure of an optical modulator. Modulators are designed to modulate either guided or free space optical waves. Like, first one is bulk modulator. It modulates free space beams. Some examples of bulk modulator are acousto-optic modulators and early electro-optical crystals. Second type of modulator is waveguide modulators. Modulated guided waves in waveguides. Some examples are integrated photonic modulators, electroabsorption modulators, silicon photonics modulators. Waveguiding enables miniaturization and integration, but it requires guided wave coupling. Now, let us discuss various advantages of various modulation techniques. First one is high data transmission rates, means bandwidth efficiency. Optical modulation allows for the transmission of data at very high speeds due to the large bandwidth available in optical fibers. Techniques like wavelength division multiplexing WDM can further increase the data rate by transmitting multiple channels simultaneously. Second advantage and most important advantage is longer transmission distance. It means reduced signal degradation. Optical signals, when modulated appropriately, can travel long distances with minimal loss and distortion. This is especially beneficial for long haul communication while maintaining signal integrity over vast distance is crucial. Third advantage is improved signal quality, which means noise immunity. Optical modulation techniques can improve the signal to noise ratio SNR, making the system more resilient to noise and interference. This results in clearer signal transmission and reduced error rates. Next advantage is energy efficiency, means lower power consumption. Optical modulation can be more energy efficient compared to electrical modulation techniques, especially in fiber optic system, as light signal requires less power to propagate over long distances. Next advantage is increased capacity and scalability, which means support for dense wavelength division multiplexing DWDM. Optical modulation techniques enables the use of DWDM, which allows multiple data streams at different wavelengths to be transmitted simultaneously. This significantly increases the capacity of optical networks. Next advantage is compatibility with advanced encoding techniques, which means advanced modulation formats. Optical modulation supports advanced formats like quadrature amplitude modulation QAM and phase shift keying PSK, which can encode more bits per symbol, thereby increasing data throughput. Next application is lower attenuation and dispersion, which means reduced signal loss. Optical fibers and modulation techniques together minimize the effect of attenuation and dispersion, which are common challenges in communication systems. This leads to a more reliable transmission. Next is enhanced security, which means signal confidentiality. Optical signals are more difficult to tap into or intercept compared to electrical signals, providing an additional layer of security in data transmission, especially in critical communication networks. Next is versatility and flexibility, which means adaptable to various applications. Optical modulation techniques can be adopted for a wide range of applications, from high-speed internet to secure military communication and medical imaging system. Next is support for higher spectral efficiency, which means efficient use of spectrum. By utilizing advanced modulation formats, optical communication systems can achieve higher spectral efficiency, meaning more data can be transmitted within a given bandwidth. Now let us discuss the disadvantages of various modulation technique. First is complexity and cost, means advanced modulation schemes. Techniques like quadrature amplitude modulation and orthogonal frequency division multiplexing are complex, requiring sophisticated signal processing. This increases the cost and power consumption of the receivers. High precision components. Techniques like coherent detection require high precision lasers, modulators and detectors, which are more expensive and require precise alignment. Next is signal degradation, dispersion and nonlinearities. Optical signals can suffer from dispersion, both chromatic and polarization mode, and nonlinear effects like four-wave mixing and self-phase demodulation. These effects distort the signal, especially in advanced modulation schemes with dense spectral efficiency. Noise susceptibility. Techniques like amplitude phase shift keying are more susceptible to noise and power fluctuations, which can degrade the signal quality. Next is power consumption, means high power requirement. Some advanced modulation techniques, especially those used in long haul communication, require higher optical power to maintain signal integrity over long distance, increasing the overall power consumption. Next is bandwidth efficiency versus complexity. Techniques that improves the bandwidth efficiency, such as high order QAM, also introduce the greater complexity in the transmitter and receiver circuitry. This can limit their practicality in certain applications. Next is synchronization and timing issue, means complex timing requirement. Techniques like coherent detection require precise synchronization between the transmitter and receiver, which can be challenging to maintain, especially in high-speed system. Next is implementation challenges, means integration with existing system. Adopting new modulation formats may require changes in existing infrastructure, leading to compatibility issues and increase deployment cost. These disadvantages highlights the trade-offs that must be considered when selecting an optical modulation technique for a specific application. Now let us discuss various applications of these modulation techniques. Optical modulation techniques are essential in modern communication system and enabling the transmission of data over optical fiber with high efficiency, speed, reliability. Here are some key applications of optical modulation techniques. First is telecommunication, which means high speed data transmission. Optical modulation techniques are crucial in transmitting high-speed data over long distances. Techniques like amplitude modulation, phase modulation and frequency modulation enables the encoding of data onto light waves, facilitating communication over fiber optic networks. Second is fiber optic sensor, means environmental monitoring. Optical modulation is used in fiber optic sensors for detecting changes in environmental conditions such as temperature, pressure and strain. These sensors are widely used in infrastructure monitoring, aerospace and industrial application. Next is biomedical sensing. Modulation techniques are employed in optical biosensors to detect biological changes such as glucose levels or the presence of specific proteins through changes in the optical signal. Optical computing or data processing. In optical computing, modulation techniques are used to encode the processed data at the speed of light, offering the potential for much faster computing compared to traditional electronic system. Quantum communication, which is quantum key distribution. Optical modulation techniques are essential in quantum communication, where they are used to encode quantum information onto light particles. These ensures secure communication channel, as any attempt to intercept the data alters the quantum state, revealing the presence of an eavesdropper. Next is military and defense. It has secure communication. Optical modulation is employed in military communication system to ensure secure high-speed data transmission. Techniques such as speed spectrum modulation, which helps in protecting signals from interception and jamming. Next is broadcasting. Cable television. Optical modulation techniques are used to transmit television signal over optical fibers, providing the high quality interference free broadcasting system. Next is medical imaging. Laser surgery. In laser based optical procedures, modulated optical signal controls the laser intensity and focus, improving precision in surgeries. These applications highlight the versatility and importance of optical modulation techniques across various fields, from telecommunication and computing to healthcare and defense. Now, the summary for this presentation: optical modulation enables the controlled encoding of information onto optical waves through a variety of schemes and approaches. The modulated optical parameters, whether it is amplitude, phase, frequency or another attribute, directly impacts the type of information that can be conveyed and recovered. Modulation is performed through the direct imposition of signals onto optical sources or via separate external modulators, each offering different trade-offs. A diverse set of physical effects, material properties, device configuration and modulation signal orientation are leveraged to achieve modulation through refractive index changes, absorption variation or other wave manipulations. Overall, optical modulation is a versatile and crucial process that underpins modern optical communication network by facilitating the transmission, recovery of encoded signal across fiber links. Thank you.